this time, but we'll go ahead and get started.
Thank you, Lynn. Let me go ahead and get the slides pulled up here. All right.
So just some logistics here. We did mute everyone on entry. Please make sure you stay on mute. And then if you would like to ask a question of Jason, you can take yourself off of mute to ask a question, or you can put a question in the chat box. Thank you.
Yeah, and please do feel free to just interrupt if you find a good time, or if someone sees a question in the chat, feel free to stop me, because I don't know if I'll be able to see the chat box while I'm sharing my screen here. But that all would be just fine with me. Okay, you guys can see the screen, right? Perfect. All right, so I guess we'll just go ahead and jump right into it then. So like I was saying, this is a pretty informal talk, but yeah, I hope you guys enjoy it, and we'll be talking about all kinds of different things NASA, some of the experiences I've had, and some of the different things that, a little bit of a historical perspective to start out. So we will just jump right into it. So today we'll be talking about some space helicopters, as I like to call them, or as the scientific community maybe prefers, planetary aerial vehicles. So here's just a slide, a little bit about me, a little bit more about my background. I started out, really thinking about aerospace probably in the 7th grade or so, when I was about 12 years old. I was in the car with my mom. She mentioned some fun fact about the gold visor of an astronaut spacesuit. I went home, I looked it up on the computer, and I found some link on Wikipedia or something that led me to aerospace engineering. And so from that day, around the 7th grade, I decided that's what I wanted to do. And so you can see I went to Penn State for aerospace engineering for a very long time, and I'm still here. Penn State's a great place, so I'm not sad about that. I started in 2013, and I did my undergrad here and then my master's, and I'm now kind of getting near the end of my PhD. So pretty soon I'll be leaving, and I will be sad to leave, but the good news is that I will head out to NASA Ames Research Center. It's in Silicon Valley, California, where I did an internship back in the spring of 16 for 4 months. And then I've interned there a few times since then, and I joined the Pathways program in 2018. So that's basically, for anyone that doesn't know, that's just a cooperative program where you go to school and pursue your degree. And then if you have breaks, whether it's in the summer or whenever you might have breaks from school, you go back to the NASA Center. And then after you graduate, you just become a full-time NASA employee. So moving right along, this thing shows, this chart just shows a couple of the different places that I've been working at and different things. I'm not going to go through all the details of it, but you guys could see a couple of them here. Bell Helicopter is one of the major helicopter manufacturers in the U.S. I spent 2 summers there, learning a lot of different things, picking up a lot of great skills with that. And then eventually I moved on to the NASA Ames Research Center. And so that was the branch that I work in is the aeromechanics office. They're mostly focused in helicopters and rotary wing research. And so that's where we pretty much get to that Ingenuity Mars helicopter. So we'll talk a little bit about that today. And then, of course, that led me to the Dragonfly program. So I have a very helicopter focused background. I really like them. They're a lot of fun. And it's a pretty challenging problem. So you see back to Bell Helicopter, I spent 4 months in Russia. I was at the St. Petersburgsky Государственный Университет, which is the St. Petersburg University in Russia, and I learned Russian, so that was fun. There's a lot of different interests for why I did that, but I really just find the language and culture pretty fascinating. I hope to use it with work someday. And then at the end, you can see where we're at present is the Dragonfly program at Penn State. So you can see a little picture of it down there on the bottom right, and we will most definitely cover that in more detail later on in the presentation. So I'll start out and just kind of briefly go through a little bit the journey to Mars with NASA. And, NASA's been teaming up with a lot of different strategic partners at looking at, hey, how are we going to get to Mars? How are we going to get people to Mars? How are we going to explore the planet more and learn more than we already know? And so just a little bit of historical background on it. In the early days, getting there, getting to Mars, getting into space, of course, was very hard, right? I'm sure most of you guys have read about or heard about the space race and all that with the USSR, the Soviet Union. But then once we kind of got into space, we said, all right, well, what's the closest thing? What's the next thing? And of course, Mars is the closest after the moon. So we started trying to go for Mars, and you can see we have failure, failure, failure in the right column here. So the first few missions were not successful. It took after a couple attempts until we could even get something to just go past Mars. So getting out there, getting farther away from the Earth and everything like that was quite a challenge. So it took us a good number of years to do that. And then from the time that we had that first flyby in about 1964 there, it took us until 1996 to get the first rover on Mars. So quite a long time. You see we have some successes in there, and I'm skipping a lot of different missions and all that. Here's just a few of the highlights, and we won't go through all of them. But the takeaway that I want you to see from this slide is that it's very hard to get to Mars, and it's very, very hard to land something on another planet. So you can see 1996, really not that long ago. I mean, I had already been alive at that point, so it can't be that long ago, right? And so there we have it, the first rover, Pathfinder, Sojourner, 1996 with the launch date. So just a quick slide here. Are we getting better at it? I think so. You know, it's a tough question. You can see that since 1996, since that first launch and the first landing there of the Sojourner rover, here's just a few highlighted missions of things that we've sent to Mars. Some of them successful, but you can see I've bolded a lot of failures. And we even have failures recently as 2016 on this slide with the ESA, the European Space Agency's Curiosity Lander. So they sent this to Mars, it crashed into the surface, and basically 260 million US dollars equivalent blew up when it crashed into the surface. So we are getting better, I think, but you know, still getting to Mars is quite challenging. So I have a few slides to show you guys the rovers that have landed on Mars before we get to the helicopters, the flying portion, just because I think that they're pretty neat to look at, and you know, if we see the capability of the rovers, we can kind of understand a little bit better where the helicopter fits into place alongside these rovers. So you can see here we have the Sojourner rover, 1996, first rover on another planet, and it was really meant to just be a technology demonstrator. So we wanted to send it there to Mars just to prove that, hey, we could send something there that can move around, take some pictures, gather some data, and all those different kinds of things. You can see in the top right here a cool image of it next to the people. I always like to do that for some size perspective. All right, so then next we have the Spirit and Opportunity rovers, which were the next ones there after Sojourner, and that was launched in 2003. You can see some 2004 landing dates on Mars. It takes about 9 months to get there, give or take, depending on the orbital mechanics at the time. And then they've been operating, you can see here, Opportunity operated for about 15 years. So it actually just recently ended its mission in 2019 when it stopped receiving signals, stopped communicating back with Earth. So it was really a follow-on to that first rover with the main goal to find water on Mars. And so we could see we're getting a little bit more sophisticated. The rovers are a little bit bigger, as you can see with my picture of the people scale here. And they're really getting to be a good bit more complicated. There's a lot of different things going on. It has all its solar panel arrays around the vehicle, some more intricate suspension systems and wheels to traverse more advanced terrain and all these different things. Then that brings us to the Curiosity rover, which is, I think that's the one that I was most familiar with before I really got involved in these kind of things. Just a name that I heard all the time growing up. The Curiosity rover landed in 2012, and it is still operational. So it's still roving around Mars and still exploring and still teaching us new things all the time. Now the mission, very similar to the previous ones, but a little bit more expanded, was to find conditions favorable to life on Mars. So the scientists believe that there's some water on Mars and there's maybe some building blocks for life, and so these rovers are really meant to go there and find out exactly, basically to prove those hypotheses and find out what exactly is there, what elements are there, could it support life, has it previously supported life, and all these different things. So here the Curiosity rover since 2011 has taken over 800,000 images of Mars, of the surface of Mars, and you can see it traveled more than 15 miles in 9 years. So I highlight that because I want you to remember that, 9 years, 15 miles. And then before we click over to the next slide, you can see here two people with the mock-ups of three of the rovers. So the Spirit and Opportunity are pretty much duplicates of each other, but you can see how much we've grown coming up here to Curiosity. And then that brings us to today. So we have the Mars 2020 mission. It just landed on Mars in February of 2021. And the mission is really to search Jezero crater for signs of past life. So you guys can start to see a trend here, right? That's why we're going to Mars. We're trying to find these signs of past life. And there was really two main things, I think, two new pieces of hardware on the Mars 2020 mission. The first one, Ingenuity, which is the helicopter we'll be talking about today. You can see a picture of it on the ground here on the bottom left. And then on the bottom right, you can see it tucked in beneath the rover, under the belly of the rover. The other new part, the other tech demonstration, is the O2 production. And I do have a cool picture of that, so we'll show that in just a second. But a machine that basically generates oxygen on Mars just from the atmosphere that, it pulls into it. And they're using that to prove out technologies for when we eventually send people to Mars. So here's a couple of the instruments. You can see this thing is getting bigger, more complicated. Just to show a few of them, these are kind of the highlights that I found when I was researching this vehicle a little bit. And I'll just real briefly flip through a couple of them. You have the MOXIE, so that's what I was talking about, the oxygen generation, and that's both for astronauts to breathe as well as rocket fuel. So we think that one way we might get to Mars is to send a rocket there, have it enter the Mars atmosphere and land, and then it would have some sort of oxygen generating machine on the surface of Mars that would replenish the fuel basically back into the rocket so that it can return to Earth. That means that we don't need all of the fuel from the time we leave Earth, and you can either send a bigger payload, have more food and supplies with you, or these various different positive outcomes of being able to do that. There's some cool cameras, the Mastcam Z. Each of these rovers, they get a little bit more advanced in the technology that they're using. We have now pretty nice colored images. We have even some video feed from the Perseverance rover. Here is a device that characterizes the Martian atmosphere. So you might be wondering, well, why do we really care about the Martian atmosphere? The two big ones for me, I guess, would be that someday if we send people there, that's a pretty important one, right? We have to know what's in the atmosphere. How can we modify it so that it could be turned into breathable air? And then the other part there too is for maybe future helicopters. So we have one, the Ingenuity helicopter that's flown already, and then eventually we want to be sending some more. But to do that, we need a better understanding of what really is the air like on Mars and what might it mean for a future helicopter design, because it's very different than it is here on Earth. So then there's a bunch of spectrometers, and I don't know, I'm not one of the scientist guys, I'm the engineer, so all these spectrometers and things, they're cool, but basically they x-ray the ground and different things, the soil, so that we can learn what kind of elemental properties are in the ground and what the sediment is made of and all different things to learn if it could support life or if it has in the past supported life. There's another one, a couple of those, we'll skip over some of those. Okay, so here is some Ames contributions to the Mars 2020 mission. So you guys can see that Ames Research Center, which is the NASA center that I work with out there in San Francisco, San Jose area, California, they have helped a good bit, contributed a lot to the Mars 2020 mission. So you can see on the top left, one of the state-of-the-art facilities at Ames is an ArcJet complex. So this is a room, massive room with all of these wires, all of this electricity cabling running every which way, and plasma and different things. And it has this very, very small test section. So they have a representative heat shield, which is maybe about, 3 or 4 inches across. And they create this supercharged plasma jet, this ArcJet, to basically simulate the entrance into the atmosphere at supersonic speeds, where you get all this supersonic effect and very, very high heat. And so they're basically testing the ablative properties of the heat shield, making sure that the vehicle is going to survive that atmospheric entry into Mars. You can see here, this is a picture of the heat shield, the backside of it, and you can see some entry, descent, and landing instrumentation. So we want to learn how good our heat shield was that we made. Maybe we could have gone with a little bit of a lighter one. Maybe we didn't need so much of that ablative material, and so on. So that was another part that came out of Ames. You can see the parachute testing on the top right. So I was actually around when they did this test. Basically, they packed the parachute in a cannon that you can see on the top of this tripod here, and we turned the wind tunnel on. So this is the biggest wind tunnel in the entire world. It's 80 feet high, 120 feet wide, and basically when they turn this wind tunnel on, so we put airplanes in there, helicopters, to simulate them flying and take measurements. When they turn this on, they have to first call the city of San Francisco and talk with them and agree, hey, we're about to flip on the wind tunnel. We need you guys to route some power to us so that we don't accidentally knock San Francisco off the grid. That's a pretty cool facility. A lot of fun when they were testing that. We have CFD on the bottom left, computational fluid dynamics, which is basically simulating how the thing would fly and using the computers to tell us how well it's going to operate. In my case, how well the helicopter is going to fly, and so on. Some software for the rover itself, how to navigate and things like this. And then on the bottom right, the Ingenuity Mars helicopter. All right, I'll just pause there for a second as I'm loading up the next slide to see if there was any questions in the chat or anything at this point. All right, I think we're good. So then getting on to Ingenuity and kind of looking at an overview of the capabilities. So remember I told you guys that in 9 years that one rover had gone 15 miles. Well, the cool thing about having a helicopter on another planet is that that same trip, many miles, we could do in a couple days. So you could see here that this entire path, which is shown as the Curiosity Rover, over a 5-year period, could be covered by a future rotorcraft in about 3 days. So the first helicopter, the Ingenuity that we're talking about today, it was sent to Mars as a technology demonstrator just to prove that we could fly a helicopter on another planet, because there were a lot of people that said, hey, there's no way that could be done. And so Ingenuity was really just to show, hey, we could do that. We could use this as a means of exploration on another planet and make it vastly more efficient. We could cover a lot of ground in 3 days' time instead of 5 years. Very big benefits there if we can pull it off. And as you will see, or as you probably maybe already know, it has been quite successful. So some of the challenges, I talked about how Mars is very different from Earth. And so here you can see the density. My understanding is that you guys are some science folks in the crowd. So I'm hoping that this isn't really new information, but the Earth density, so basically how much mass we have in a certain amount of space on Earth, is 1.225 kilograms per meter cubed. So right, if we had a meter by a meter by a meter cube, it would weigh 1.225 kg. Now on Mars, that same cube, the air is so much thinner that it would only be about here, the 0.017. So I think it's about 0.7% the atmospheric density on Mars as it is on Earth. And then combine that with temperature swings that can go down to negative 50 degrees Celsius on average, and you get a pretty harsh environment. So we have to be able to design to that. Another thing, we have the autonomous control and navigation. So this helicopter, it's too far away. It takes, I don't know if it's minutes or hours, I guess, depending on where Earth is around the sun and where Mars happens to be at any given time. But there's no way we can have a pilot sitting here on Earth flying this thing. So the vehicle has to be able to think for itself, fly itself. If any problems arise, it has to be able to recognize what happened, come up with a solution, land the vehicle safely, and all these different things. So here's a couple, just a timeline of some of the development of that Mars helicopter at Ames, at NASA Ames. And you can see back here as early as 2015, they started to involve the Ames Research Center in this idea to send a helicopter with the Mars 2020 Perseverance rover. So it was really not all that long before the mission actually launched that they decided to really start looking into this. So very quickly, a lot of the researchers out there at Ames got things spun up, and they started doing, you can see here, some different test stands. This one in the middle here is actually in a tunnel that we can pump down, so we can simulate the low pressures and the low densities associated with the Martian atmosphere and test the helicopter blade, test helicopter rotors in that reduced atmosphere environment. Here again is a wind tunnel that they built and put inside of that room where we can suck down the pressure. And so again, testing the rotor performance, figuring out how much power we would need to fly, and these different things, because the helicopter blades, they perform very, very differently in that Mars environment than they do on Earth. So here you can see we have some of the computational fluid dynamics. Some folks like to call it colorful fluid dynamics just because it makes pretty pictures. Although it does tell us a lot, teaches us a lot about how well the vehicle is going to fly. And then here you can see we're starting to look at some more advanced concepts. So once the mission has been launched, Mars 2020 at this point was already on its way, they immediately started looking at some future concepts of how we might carry more weight, how we might carry more scientific instrumentation, because at the end of the day, that's really why we're going to Mars, is to learn about Mars and to do all these things. So any helicopter we send, it should be able to carry some instrumentation that's going to tell us and teach us about Mars. You can see a few of those there. And then down here on the bottom of the timeline, around summer 2019 or so, Dragonfly, the project that I work on the most, was accepted and fully funded from that point on. So a few specs of Ingenuity. Here is the helicopter, the first helicopter to fly on another planet. You can see it's quite small. The fuselage here is just a little box, right? Because on the way the rotorcraft aerodynamics work is that the thrust equation or the lift equation, how much weight we can lift off, is proportional to that density. So if the density is 0.7% of what it is here on Earth, it means for the same helicopter blade size, we can only lift about 0.7% the amount of weight that we would be able to lift on Earth. We would be able to lift 0.7% of that on Mars. So in there it has the batteries, the sensors, the avionics, the communication to the rover, and all these different things. You can see a little rectangular solar panel on top, so it'll actually sit for a day and recharge itself, and then usually one day I think is good enough to kind of get recharged up, and then we can do another flight. And the blades here, of course, you can see with some pretty advanced control systems. So they have full authority. They can tilt in all directions, just like a normal helicopter would. And you'll notice that there's two of them, so we call that a coaxial configuration, mostly just because of the packaging. It makes it so that we can make the smallest package and fit it on there and kind of bum a ride with that Mars 2020 Perseverance rover. So here's some testing. We have some cool videos. This video is basically, they wanted to test, can we lift off the ground with a helicopter in a Martian environment? So this is inside the Jet Propulsion Laboratory Space Simulator. They have about a 25-foot diameter facility where, and this is a different one than I was previously talking about, where they can pump down the pressure and they can simulate the Martian environment. So we have the helicopter in there, and we wanted to see how well it would fly. So I'm going to try to play this. We'll see if it comes through. So here you can see it's kind of bouncing around, and there's no control system yet, so we're just spinning the blades faster and seeing if it's going to lift off, and you can see it's lifting off. And then eventually, since we don't have a control system with a feedback loop, eventually we crash it. So it's still flying, still doing pretty well, but it will be coming when the thing kind of just smacks into the ground. There it is. So all right, we proved that you could fly in that reduced atmosphere. And then the next thing to do is make a control system. So they went ahead and did that. We made a control system for it. I'll skip ahead a little bit here. So now you can see the helicopter is actually lifted off, and it's controlled at this point. So we have some feedback loops in the control system. We're able to steer the thing and keep it in one place. You can see all these little white dots on it. So we have cameras all around the room, and that's how it knows exactly where it is within the room. The cameras are sending information to the vehicle, and then the vehicle's control system is deciding, okay, I've drifted a little bit to the right, let me adjust and move back over to the left. So they proved that, okay, we can fly in the Mars atmosphere, we can have controlled flight in the Mars atmosphere, and I think that's kind of all we want to show. Here's one more video we'll take a look at. So this is really the built-up configuration with solar panel and all. And there you have it. There we are hovering again in that space simulator. So this video, you can see they commanded the vehicle to translate 1/2 a meter to the right and hold that waypoint. So sit there for a second, and then eventually it'll tell it to come back over and do a controlled landing. And so they're kind of working the systems, making sure everything is working properly. You can see right there, it just yawed, so it's spun 180 degrees while holding its position, its fixed position, and then it returns back to the starting point. So here is a picture of the Ingenuity helicopter underneath the belly of the lander. You can see on the left side is a computer model kind of showing how everything is packaged. And then on the right side, after that safety hatch has kind of been jettisoned there, you can see the helicopter still tucked up under the lander. And so this picture was taken on Mars. I guess Perseverance kind of tuned one of its arms around and bent it around and took a picture underneath. And I remember this whole deployment process was several days long. So they would blast off that cover. They spent a couple of days looking at pictures, making sure everything was okay. And then they would slowly actuate the helicopter down to the ground. And there were several steps to the deployment, and it took a good bit of days, but eventually we got it down. So here's an image showing just the field location of where the Perseverance rover and the Mars Ingenuity helicopter were heading to. You can see on the right side, Jezero crater, and there it is on Mars. We have a couple of these, but we'll kind of pass through those. We have cooler charts than these ones. All right, so here is a video of the first flight on Mars by that Ingenuity helicopter. So this was taken by the Perseverance rover with some of those more sophisticated cameras that it's getting, and I think the video quality is okay. I mean, I always kind of wonder how come we don't get like high definition videos of this thing flying, but I think it's just because that would take well too long to send back to Earth, is my best guess on that one. But there you go, you can see it. Pretty good flight. Moves around a little bit, does some of that directional control to make sure everything's working, and that's about it. So there was first flight on Mars, first flight on another planet by a heavier than air vehicle. And then here's a video we have of the fourth flight. So this every time it got a little bit more advanced, pushed the limits. So really the interesting thing, actually we have sound on Mars recorded by the rover. I don't know if you guys could hear that. I think there's a low rumble. There you go. Maybe you can hear it. Should be coming from the left side here. There we go. So what I was going to say before we played that one was the purpose of this helicopter, like I was talking about before, was really just a technology demonstrator. So we just wanted to prove that it could fly, that we could explore another planet with a helicopter. And so there was originally 5 flights planned. So it very successfully, very quickly finished all of those flights and then did much more after that. So we'll try to jump forward here. You can see this chart, I haven't updated it yet. We actually do have more now. But this covers the first 8 flights. So from April through June, it had done the original 5, and then an additional 3 beyond that, and every one has gotten a little bit more intense than previous ones. So you can see the horizontal distance that we flew on each flight. So we started out, first flight just a hover, we just lifted up and then sat back down. Then next we moved 13 feet, and then 300 feet, 800 feet. So you can see that, by the time we've gotten just a couple flight tests into this mission, we've covered what a rover would take, I don't know, maybe several months or maybe years to cover in that same amount of time and that same distance.
Jason, we do have a question in the chat.
Sure, yeah, thank you.
Ariana says the mechanic design reminds me of drones that are controlled by a remote. Is it possible to helicopter a rover with a remote? Can you control it with a remote?
So this one, yeah, theoretically you could control it with a remote. Like if we were here on Earth, you're right, they do have a lot of designs you could buy in the store, or you could buy very expensive toy helicopters that you could control with the little remote control of this design. And I think the reason for that is that it's very stable. It has those two rotors that have the forces equal and opposite to each other, so it is quite easy to control. The challenge of why we can't actually have a person flying it here on Earth is just the time delay. So when we have this helicopter and we then shoot it to Mars, now it's the time delay, so it takes us several minutes to I think it's 2 hours, and maybe someone else knows that one off the top of their head, but I want to say it's about 2 hours from the time we would send a text message on Earth to when it would receive a phone on Mars. And so for that reason, we can't have someone sitting here flying it, because if I'm seeing the video screen and all of a sudden I see that there's a mountain in front of my helicopter, well, that was 2 hours ago. So then if I tell it, oh no, move left and punch it and climb out, it takes 2 hours for that signal to get back. So it's 4 hours later, the helicopter has long since crashed into the surface. So for that reason, the helicopter has to be able to think by itself, fly by itself, and yeah, it makes it a very much more complicated problem just because of that time delay. Good question. All right. So here you can see a couple of the kind of future concepts that they're looking at right now. So the folks out at Ames, and JPL, they're looking at, all right, well, what's next now that we've proven how well we can fly and that we can aid the scientific mission with this thing. So the Ingenuity helicopter has actually furthered the mission, and really kind of bolstered what the Perseverance rover has been able to do. So it's scouted different areas and trying to determine which areas might be most interesting for us to drive the rover to, since the rover is really what has all that instrumentation, all that scientific instrumentation. So it's been very much a help already to the scientific mission. And they're looking at, well, should we do a similar configuration but just a little bit bigger, or should we make it similar configuration but a lot bigger? So you can see that the mass here of this vehicle is 20 kilograms, whereas the Ingenuity is about 1.8 kilograms, about a factor of 10 larger. And then here you can see a completely different concept where it's more of a distributed propulsion system. So we have about six rotors there, a hexacopter, all spread out in different areas. And this is a little bit more efficient, so you can, for the same amount of power and different things, you can fly pretty well. The problem there is that it takes up much more space. So when we launch it on the rocket, we need a pretty big rocket to carry that one and to fit it to get over there to Mars. So here is a slide on the entry, descent, and landing, and that goes into some mid-air deployment there. And so this is just kind of showing, well, what happens when we come into the atmosphere on a future rotorcraft. So if some of you guys saw, maybe when we came in with this Mars 2020 mission, there was actually a sky crane that had rocket-propelled engines on it. And so this thing carried the rover and Ingenuity. It brought it down to the surface, and then it had a crane that literally lowered the whole Perseverance Ingenuity system down to the ground. The tethers broke, and they broke them off, and then this little jet propulsion thing flew off and flew away. So that's very complicated. It adds a lot of mass into the spacecraft that we don't really necessarily need if we have a helicopter. So you can see here the idea is that we just jettison the heat shield once we're safely inside the atmosphere, and then the helicopter just lets go, spins up the rotors, and it flies away. And then it comes down to a nice landing on the surface. So this is kind of what they're looking at now. That's maybe the future direction, and it would allow for a bigger helicopter because we don't need that crane portion with all the rocket propulsion and everything. And you'll see in a little bit that this is actually exactly what we're doing with Dragonfly on Titan. So here's just a couple milestones, kind of brush over these, but the Ingenuity helicopter is the first powered sustained flight on another planet. It's not even just helicopter, but first of anything to fly on another planet. Very, very successful so far. It's still going very strong. I believe it's on flight 14. So they planned 5. We've done over 14 already. And then the rover has every single rover gets bigger and better, as you guys saw earlier on. And this one is working to further kind of answer those questions about signs of life and oxygen for astronauts and all that great stuff. Here's a slide just showing some sample return. So eventually we want to grab some sediment from Mars and shoot it back to Earth, and a couple of different of the possible configurations here. So the Mars 2020 Perseverance rover does have a little piece of it where it's going to be collecting samples, and so the idea would be that eventually we send another spacecraft to Mars, meet up with that Perseverance rover, get those samples, and then shoot them back to Earth so that we can really analyze and very carefully do some scientific experiments to learn what exactly is there. Okay, so then moving on, we will hit the NASA Dragonfly portion of the talk here. So Dragonfly is what I mostly work on. This is my day-to-day job here at Penn State, and we work with some of the folks out there at NASA Ames, and the principal investigator for the project there, that's the Johns Hopkins University in Maryland. And so you guys can see here, this is another planetary aerial vehicle, or as I like to just call it, a space helicopter. So you can see we have our fuselage, a radar on top, a bunch of little rotors. So instead of 2, like we saw in Ingenuity, this one has 8 in total. So 2 on the front corner, 2 over here, and 2 and 2. So kind of a mission overview of Dragonfly is, well, we have an $850 million contract from NASA. So it's one of the New Frontiers missions, and the way that works, NASA every so many years puts a lot of money to fund a program. Well, they basically put out a call for proposals. So they say, hey, to the whole scientific community, we're going to do one of these competitions. We want you guys to propose some things to us, where you want to go explore, how you're going to do it, etc. And so after this huge competition with many different teams, the Dragonfly team won this most recent round of the funding. We got $850 million to build this, to design it, to build it, to launch it. And we have a launch date planned for the late 2020s. So then from that point, we said to get to Mars, it takes about 9 months. Well, to get to Titan, it takes about 7 to 10 years to get there. So that's quite a long time. And you can imagine these motors and the blades and the electronics sitting on the shelf for 10 years and then having to work as soon as they get there the first time. There's a lot of design considerations that go into this part as well. And we do expect a arrival in the mid-2030s. So you might be wondering, well, why are we interested in Titan? Okay, we get Mars. Mars is the closest thing to Earth besides the moon. So that makes sense, but why Titan? And the answer is really that the scientists believe it's the most Earth-like planetary body in the entire solar system. So, of course, you guys know what Earth looks like. And then down here on the bottom, we have a somewhat artist rendering, but also based on scientific studies and scientific information of what it might look like on the surface of the moon on Titan. So you can see some mountains, and of course there's Saturn in the background, and then we have some lakes and rivers, and that's really what the scientists think is on Titan. So you see Mars is this desolate wasteland, it almost looks like, and then here you could mistake this for some mix between a mountain range and some river canyon. So that's why we're so interested in it. And you can see here in the middle of the screen, Titan shown somewhat size appropriately to Earth there. And then on the left side, you can see a picture that was actually taken on Titan. We had sent a probe there, the Huygens probe, landed on Titan in 2005, and just didn't really survive that long, but it took a little bit. It took a couple pictures, took some information, got some data on the atmospheric properties on its way down to the surface. And so that's how we're more confident that our helicopter is actually going to work. It's actually going to fly on Titan. And here you can see the last bullet, Dragonfly's mission, the main mission, to explore Titan's prebiotic chemistry and habitability. So are there building blocks that could support life? Has there been life there? Could there be life there? These are the questions we're really trying to get to.
Jason?
So that's great and all. Titan's cool, Titan's interesting. But why a helicopter? That's really the question. Why not a rover? Why not something that we're really good at? We just flew this helicopter on Mars for the first time, and then now all of a sudden we're making this beast of a thing. And just for your guy, when on Mars just a few months ago we flew a 4-pound, 5-pound helicopter. So a very big difference, and the reason that we think we can pull it off is that Titan has two very good things going for it. The first one is that the gravity on Titan is about 14%, or I think it's about 1/7 of what it is here on Earth. So if you jumped, it's like on the moon, you can jump really, really high if you were on Titan. So just a corollary, someone who weighs 200 pounds on Earth would weigh 28 pounds on Titan. Now, the other thing is the atmosphere, and I skipped that bullet, that's the first one. Titan is a much thicker atmosphere, so if you imagine when you're running through, you're running on the street, it's pretty easy. But if you jump into a pool and you try to run, you're met with all this resistance. You can't move at the same speed. In fact, it's even just hard to pump your arms when you're in the water. We have a similar thing on Titan where the atmosphere is somewhere in between the two, somewhere in between air and water. And so what it means is that our helicopter is very, very efficient. The wing can push a lot of air out of the way and create a lot of thrust to lift up our vehicle. So when you combine the two of these, it is very easy to fly on Titan. So if we had an equivalent helicopter here on Earth, and then we move it to Titan, it can carry about a vehicle that weighs about 28 times more mass. It has 28 times more mass than what it would have on Earth, and it could fly the same in both places. All right. So here we are at the arrival at Titan and projected for the mid-2030s. And you guys could see on the left side here, kind of a little bit blurry, sorry about that, but you could see the left side, we have the aeroshell. So this is basically how it launches on the rocket and the cruise stage that's going to support it along that journey. So it has some thrusters to make sure that we get the proper trajectory to Titan and everything like that. And then we'll go ahead and do our ballistic entry into the atmosphere. And you can see a kind of a sketch of the Dragonfly vehicle tucked in there inside the aeroshell. So if we move to the right side here, you see that we've entered that atmosphere, we've deployed our parachute, and at this point, we're falling underneath that parachute descent. And then like we were talking about with the future Mars helicopters, we're going to do some type of mid-air deployment. In the Dragonfly program, we call it transition to powered flight. So we let go of the back shell, we let go of the parachute, and we let the thing just free fall for a second, right? Because we have to get away from that parachute so that it doesn't come back and whack us. So we fall for a good second, and then we start to turn on the systems and spin up the rotors, and then you can see it kind of dives forward a little bit and dives away from the parachute and everything like that. And then it just flies away and flies down to a nice soft landing on the surface of Titan. And so that's the scary part, is that, we're going to have this thing in a capsule all tied up like this for 10 years, 7 years. And then when it gets to Titan, once we enter the atmosphere ballistically like this, there's no going back. Everything has to work, or we're going to crash $850 million into the surface of Titan. That would be very bad. We're going to try not to do that. We need a lot of smart people to do that. So you guys keep that in mind. Come back, and once you're done with school, come work for us and help us do that. We also want to study the atmosphere for the same reasons as before on Mars, so that we can better adjust our scientific understanding. And also, if we ever sent a vehicle there in the future, we'd be able to make a better vehicle to fly on Titan. So if you're wondering then, how do we fly on Titan? Again, it's autonomous, because this is even farther. So it takes a very long time to fly to get a signal from Earth to there. So again, the thing has to completely fly itself. We basically say, hey, you're over here. We want you to go fly over here. And while you're doing that, kind of scope out the area, take a look at different landing sites, and try to learn a little bit about where you might go next time after that flight. But other than that, the thing is flying itself, and we have to program all of that ahead of time. So here's a picture of what I do on the program. And I'll try to start wrapping things up here so we have some good time for questions at the end. What I do is, like I was talking about earlier, that computational fluid dynamics. So we use the computer program to simulate, and I don't know if you guys could tell or not, but this on the right side, this is the Dragonfly Lander. We use this to predict how well the vehicle is flying on Titan, so we can simulate in the computer as if this is the Titan atmosphere and different things like that. So you can see this car here in the wind tunnel. We have these smoke lines that show how the air moves around the car. Well, here in the computer, we can do the same thing. So we have these lines, that shows how the air is moving around the vehicle. And here's the back shell right after that initial release, and all those different analyses going on. Here's some more of what I do. This is, if someone has a question on it about what exactly CFD is and what we're doing here, I would be happy to answer that, but I won't bore you with it just yet, so we'll skip this one for now. But on the right here, you can see kind of an old picture, an old sketch of what the vehicle looked like closer up. Another thing I do is vibrations. So the vibrations on this thing is a really big challenge for us. We have 8 different helicopter rotors all spinning around, carrying a very large vehicle. And so basically what we're looking at is rotating beams and the vibration of those beams, and it's a very, very complicated problem. I remember when I was a freshman or sophomore at Penn State in aerospace engineering, I said, hey, what are really the cool problems to solve? And I met a professor here, one of my very good mentors over the years, and he said, well, helicopters are, it's this thing that flies that really should not fly, because you think about it, it's just always trying to beat itself up, and the blades are moving every which way. You get really complicated aerodynamics and complicated structural dynamics, and so that is a very fun problem, and those are the things that I work on mostly. So what's next for the vehicle? Well, we're gonna keep simulating, we're gonna keep testing. We go into the NASA wind tunnel sometimes. Here you can see some neat pictures showing the NASA facilities. I believe this one here is out at Langley, Virginia. And basically, we have this huge fan in here. It pumps the air through the tunnel. And then in some other part of the tunnel, we have that helicopter, and we can simulate as if it's flying. There's even a NASA facility where we can pump up the density to approximately, I think, 75 or 80% that density of the air on Titan. So we said it's a lot thicker, the atmosphere, and so we have a wind tunnel where we can actually simulate that. So we do a lot of that, a lot more testing and things like this, and keep iterating, keep making it better. And then at the bottom here, you can see, find some more people to be on the team. The project is over 100 people already. I don't know the exact number, but it's a very, very large program. It's almost like a small company that's working on this. And, we're always looking for more people. So if you're interested, reach out to some folks at NASA, apply to NASA internships, and tell them you want to do Dragonfly, and we need you. Here's some lessons learned. I don't know. We'll skip that for the most part. The only one I'll say is, resiliency for me is our greatest asset. I applied to NASA many, many times, 3 to be exact, before I got offered an internship. That felt like many to me. I applied once, I never heard back. I applied a second time, I never heard back. The third time that I applied, I thought I never heard back. It was several months later. One day I randomly checked my email on a Saturday morning at like 8 a.m. I don't know what I was doing, but there was an email from this guy at NASA Ames, and he said, hey, we're with this rotorcraft aeromechanics office. We work and specialize in helicopter aeromechanics. Would you like to come out and work with us for a few months? And I said, hey, okay, that sounds pretty neat. So keep at it. Even if you don't get in the first time, just keep at it, and you'd be surprised what you can work out. So here's some more info on NASA. If you guys want, you can feel free to scan some of those QR codes. I'll leave these here for a second. And that's kind of it, guys. So I could, there's more slides I could go through, but maybe we could see if there's any questions there in the audience.
Thank you, Jason. And yes, we want to give particularly our students who are listening in our opportunity to ask questions. And thank you for the comment about resiliency, and keep applying. We've done very well in Nevada. We've increased our number of NASA internships, and Nevada Space Grant will fund a good portion of these. And the aeromechanics person or the person who handles the internships for aeromechanics was actually from Las Vegas, Nevada. So she wants to see more Nevada students get involved in aeromechanics and rotorcraft. So Marcy, did you want to moderate who has questions?
Sure. We have one asking that for your new project, the Dragonfly, since it can carry more weight, does that mean it can have more advanced picture quality, or does that have to do with the timing of it coming back to Earth?
This is a really good question, and unfortunately I don't know the answer to that, but I wonder this myself all the time, so I'm gonna find that one out I will email you guys what I find out, and then if you're able to pass that on to, the attendees or whoever was invited, that would be great. But my guess is that it's how long it would take to transmit it, because I know that we still use very simple radio frequency communication even to Mars, and Titan is much, much further. We obviously have the right technology. We have very good high definition cameras just here in my laptop that's the size of a pinhole. So I think we have it. I think it must be that it's just a communication delay with how far it is. But I will find this out.
Okay. We've got another one asking about when you recover samples in situ to bring back to Earth, how much time does it take? And economically, is it feasible? Would it be more of a possibility to have a lab in space?
So that is a very good question. And on Mars, we were seeing it's about 9 months away. So if we were to do sample return from Mars, that takes about 9 months to get back. You can cheat a little bit. So if you have the proper orientation of Earth and Mars around the sun, and you have a really, really powerful rocket, maybe you could speed that up to 6 months or something like this. So you could shorten it a little bit. But so for Mars, it makes sense. For Titan, it takes 7 to 10 years to make that journey, so it's really probably not too feasible. By the time that gets back, maybe we'll have moved on to other things. Maybe we already found life somewhere else and we forget about Titan altogether. I don't know. But the Dragonfly Lander actually has on board a device that will take the soil from the ground. It puts it into a little beaker tube, and then it has a mass spectrometer on board the vehicle. So it can actually analyze that soil right there, just like you said in the question. It has a machine inside that's going to do exactly that. So it's almost like a mobile chemistry lab, and that's a pretty neat approach. And then it'll just beam back the data that it comes up with back to us here on Earth.
So do you believe that there's life in Mars that hasn't been found yet?
Oh boy, on Mars, I don't know. That's a tricky one because we've been there for a while. We've had a lot of rovers. We haven't seen any little Martians come out and interact with our rovers yet. So maybe on Mars, I'm not so sure about it. At one point, sure, maybe. I don't know, but I think somewhere out there, I think there has to be, just statistically speaking. And whether we'll find it or not, I don't know. Maybe it's much, much, much farther away than Mars or Titan or anything else within our reach. But yeah, so we'll see. Stay tuned.
If you know and or are able to discuss, what type of control is used by the Dragonfly rotorcraft flight software, PID, LQR, etc.? Is there adaptive capacity of that at all?
Sure. All right, yeah, so thanks for the question. The controls aspect is not something that I really focus on. So there are some groups here at Penn State and Johns Hopkins that do much of the control algorithms and things like this. So I don't really know a whole lot about it. And so I don't think I could really get in trouble for saying anything because I don't really know what they're actually doing. But my very small understanding of the way the control system works on the vehicle is that it's kind of similar to a very standard EPSCoR controller. So back early on, a long time ago, many years ago, in 2017, 2018 timeframe, early in the program, we were using a very basic control method to do the control of the vehicle. I know that the Johns Hopkins folks have been working on this a lot. They've been really getting it more advanced and more capable to handle different things. And to that extent, I'm probably not really supposed to say what exactly they're up to, and I don't really know what they're doing anyway, so I think we'll just leave that one there.
How often do you find your simulations not matching the flight test?
This is a good question. So this is the trouble. They always say that no one believes the simulation, or no, they say everyone believes the simulation except the person that ran it, and then everybody believes the wind tunnel experiment except the person that did the wind tunnel experiment. And so I guess, I don't know, you have to have validation. And so that's a big key of the program so far, is that everything we do, we're coming at it with several different approaches. So I do my simulations in the computer and I get the answer. And then we have someone that goes into one of these NASA facilities, one of the wind tunnels, and does the same experiment in real life, and they get an answer, and then we compare the two of these, and we know that the wind tunnel is pretty good, it's pretty realistic, but there's still some error and some uncertainty associated with that. And then my simulation, of course, could have errors and uncertainties associated with that. So we look at the two of them, and we use this as a method to kind of reduce the total uncertainty and try to get as close as we can to what the true answer is and what we can really expect to happen on Mars or on Titan. There's a lot of cross go back and forth looking at the different things here.
Okay. And I think we have a comment here that it might be more for Lynn for a future speaker, interest and focus on the analysis of the kind of materials in space and of course Mars. So that might be something you want to look for in the future. And that is it, I believe, for the questions in the chat.
We have one person with their hand raised. If you want to unmute your mic, and Kian?
Hello. Yeah, it's Kian.
Kian.
So I am actually an intern at the aeromechanics branch. So and I'm also from Las Vegas. So like worlds combined right here. I guess my question is, I know for the Mars Science helicopter, we're just throwing the wind tunnel into that vacuum chamber in 242. Do you know if there's a similar setup for how you're going to do the testing for Dragonfly?
Yeah, so that is a very good question, and thank you for that. And I do very well recognize the room behind you. I can tell that you're on the NASA premises right now, it appears.
Yeah. 243.
Very cool. Yep, very cool. So I've spent a lot of time in there. But to answer your question, yeah, we do have a NASA facility, as it so happens, that is very close to simulating the conditions on Titan. So there's the Transonic Dynamics Tunnel at NASA Langley in Virginia. And this wind tunnel, they actually pump out all the air and they replace it with Freon. So Freon is, the stuff that goes in your car radiator. It's like a very thick, sludgy kind of air stuff. And it's basically used for AC, for air coolant. And so it has a density of about 4 kilograms per meter cubed, whereas air is 1.25 or so. And on Titan, it's about 5.4 kilograms per meter cubed. So with this wind tunnel, we can get to 70 or 80% of the actual density of what we're going to expect to see on Titan. So that means we can pretty much match our, and it has a lower speed of sound as well. So we can pretty well match our Reynolds number. We can get very close on things like Mach tip number, total thrust, power requirement. And so we're getting most of the way there. And then that's how we're going to validate our models. So we're going to do testing in Earth's atmosphere. We're going to do testing in the TDT atmosphere. And then by that point, we should have enough data where we can say, with beyond a reasonable doubt, hey, we're pretty confident in our simulations on Titan's atmosphere. And so that's kind of where we're at. The tricky part, I would say, is the temperature. Even though we're able to simulate most of the density change in TDT, it's going to be room temperature or so. Titan is cold. Titan is very, very cold. It's about negative 180 degrees Celsius, if I'm not mistaken. And it's like 90 Kelvin. So quite cold. I don't know that we really have anything here on Earth like that. And it's very challenging because we don't even know how materials behave in these temperatures. We're not allowed to use composites. So the Mars helicopter rotor blades, they're made out of carbon fiber composites. We can't use those because it's too cold. They'd be too brittle. Materials like aluminum and titanium, we have to dig into all of this literature and find out, hey, how's this going to behave? Because the yielding stress and the ultimate stress and the vibrations are all going to be different when we change the temperature 200 degrees. So that's one of the unknowns that we're really getting into now, and we're trying to figure this problem out. And that I'm not sure how we will test that, but I know the program is considering different ways that we can reduce risk and prove out how we address that temperature as well.
Sounds good. And are you guys, I know you said the Dragonfly is about the size of an SUV. Are you guys planning on doing full scale testing, or are you just going to scale it down to like 1/2, 1/3, or however big it needs to be to fit in the wind tunnel?
Mm-hmm. Yeah, that's a good question. I don't know that I can really say too much on that one, but what I probably can say is that so far we've tested rotors that are similar to the Dragonfly setup, and we've tested them in air. We're planning to go into that TDT wind tunnel with the actual, very similar to the Dragonfly rotors themselves. So we're testing some real full-scale hardware. Of course, it'll be different than what's actually going to fly on the vehicle, but the airfoils and blades and things like this are about where we're at with the true vehicle. As for the full vehicle, I'm not really sure. We'll have to wait and see what happens with that one. But yeah, there's some we'll definitely get more advanced as we go along and add as much as we can to those wind tunnel tests.
Cool. Thanks for answering my questions. If I'm still around when you transition into the civil service, hopefully I can meet you in person.
Very good.
Thank you so much.
Sure. I'll look forward to it. Thank you.
Okay, it looks like I haven't kept up with the chat because every time I try to reduce the chat, I end up closing my window. So that's why I'm leaving it for Marcy. If we have any other questions?
No other questions.
There are a lot of people who said thank you very much. I have one question for you, Jason, and this is going to be a little bit out of your area that you're working on with the Dragonfly. What's the life expectancy of the power source, and is there any thoughts on maximum flight length as far as time that could fly on Titan nonstop?
Yeah, sure. So my understanding of the MMRTG, that nuclear power plant, is that it would very well outlive the planned life expectancy of the lander. So the lander is meant to do a certain number of flights over whatever it is, maybe a few months, maybe on the time scale of a few years. I'm pretty sure the MMRTG could almost go on for, I don't know, I'm just guessing here, but tens of years or hundreds of years. It works just by radioactive decay, so I guess it depends on how much of that radioactive material you put there to start. But yeah, I think it would very well outlast it. So that's an interesting thing there. And then on the other side of that, related to how long we're able to fly, these are a lot of questions that I don't know how good of an answer I'm allowed to give, especially since we're recording this. So I'll kind of choose my words carefully on that one. But we plan to cover several kilometers at a time. So, we showed that Mars Ingenuity picture where the rover took 5 years to go a couple kilometers, and then the Ingenuity, or a future Mars helicopter, could do that in 3 days. We plan for a single flight to cover multiple kilometers. So quite far when you compare it to what a rover would be able to do in the same amount of time. And then, you consider that, we do that one time, we gather all our data in this new location, we charge up again, we let the power plant just charge it up, then we do the whole thing again, basically fly a whole city over, a couple kilometers more, and take some more data and keep jumping around like that.
Okay, thank you. Well, from all of us here in Nevada, I would like to sincerely thank you for your presentation and information. And for our students, please go to intern.nasa.gov. You see all those wonderful links that Jason provided you with, and consider submitting an application. Going to a NASA center and actually working with these NASA scientists is hugely motivational. We've not had any intern come back. Yeah, there's Kian with the thumbs up. It's highly motivational. It introduces you to a NASA scientist. And if you get excited and motivated and work with these NASA scientists and they see that you're a hard worker, it gives you a really good opportunity to then join the NASA team after you finish your degree. So I cannot say enough about applying, and we also offer scholarships for undergraduate students through Nevada Space Grant and graduate student fellowships, and those announcements will be coming out late October, early November, with applications due late January or February. For the intern.nasa.gov, they are looking at people right now for spring semester, so applications for summer internships are usually close out in early March, so highly recommend you go to that website and start applying. And any final words, Jason?
Yeah, sure. Yeah, I'll just add, one thing. You mentioned the internships and applying to those, and for me personally, I came from a very, very small hometown, and we had about 8,000 people. And so, I grew up and I was this little kid, and I said, hey, one day I'm going to work for NASA, like I told you guys from the seventh grade or so. And everyone in my hometown thought I was absolutely crazy. I mean, impossible for someone from where I grew up to go off and do that one day. So, if you guys are there at school and you're any doubts about whether or not you would be able to fit in there at NASA, I would say just go for it, really try after it, and like Lynn was saying, you get out there and work as hard as you can, and you never know what could happen. I mean, I got out there one time just because I worked very hard at Penn State, and I kept applying until they got sick of hearing from me, and they finally said, all right, come on out, we'll give you a shot. So I got out there. I worked very hard, and it was really helpful to me. I learned so much in a very short amount of time, learned a great deal, and then they decided to keep me around for a while. I definitely encourage you guys to look into that. Even if you think your chances are low, please do apply. If you don't apply, your chances will be very low. So
Yeah.
please do that.
And I'll add to what Jason said. I came from a small community in Pennsylvania too, actually a village, total of about 40 people. And, you know, you just gotta say, I can do this if I really want to do it. And that is what people look for. It's not where you came from, your background, and they want to see someone who's trying hard and has a skill set that will match with what they're looking for. And they bring people in to do a number of things. We had a UNR student who did an internship with NASA's communications department, science communications. So you don't have to be an engineer, you don't have to be a microbiologist or anything like that. There's a lot of different opportunities, so go for it. Okay, well, with that, we will close our inaugural NASA Speaker Series here in Nevada, and we're going to try to do this every other month or so, and so watch for future communications. Jason, thank you once again. Truly appreciate your willingness to talk to us, and a lot of students are commenting in the chat. Thanks so much for the motivation. So I think you've sparked some interest for these students, and we're truly appreciative.
Sure thing. Yeah, thank you very much for having me. I had a lot of fun today.
Okay. All right, everyone have a wonderful evening, and we'll see you next time.
Thank you.
Bye bye. Thank you.